Have you ever wondered how a fan doesn't just spin in place, but also manages to sweep side to side, cooling an entire room? It's not magic, it's clever engineering, a blend of simple mechanics and smart design. The main job of a fan is simple: move air from one place to another, creating a refreshing breeze. When you're hot, the air near your skin gets warm and stagnant, making you feel even hotter and uncomfortable. Fan blades, shaped like miniature airplane wings, push that warm air away and bring in cooler air, helping your sweat evaporate faster and making you feel instantly cooler. But if a fan only blew in one direction, only one person or one spot would benefit from its cooling power. That's where oscillation comes in, a fancy word for swinging back and forth, spreading the breeze around. By sweeping across the room, the fan shares its breeze with everyone, creating a more natural, comfortable airflow that mimics a gentle wind. This side-to-side movement transforms a simple personal fan into a room-wide comfort machine, making sure no one is left out. So, how does a spinning motor create this sweeping motion that feels so effortless? Inside the fan, a clever system of gears, levers, and pins work together to transform the motor's circular motion into a smooth back-and-forth sweep. It's a mechanical ballet hidden inside that plastic case, with every part moving in perfect harmony. Let's grab our tools and take a closer look at the first and most important part, the electric motor, the heart of the fan. We'll see how a simple spinning shaft becomes the start of the fan's dance, setting everything else in motion. The secret lies in how the fan's design cleverly uses one motion to do two jobs at once, spinning the blades and swinging the head. Ready to see what's inside? Let's get our hands dirty and explore. Let's dive in and discover the hidden genius behind every cool breeze and see what makes this everyday appliance so remarkable. The journey starts with the electric motor. Let's open it up and reveal the magic within. Everything starts with the motor, the powerhouse of the fan. Without it, nothing would move, and the fan would just be a static object gathering dust. Plug it in, press the button, and electricity flows into tightly wound coils and powerful magnets inside the motor, creating a magnetic field that spins a central shaft called the rotor. This process is almost instantaneous, turning electrical energy into smooth mechanical motion. This spinning shaft is the source of all the fan's motion, acting as the heart that keeps everything moving in perfect rhythm. The front of the shaft is directly connected to the fan blades, causing them to spin rapidly and create a refreshing airflow that cools the room. Faster motor speed means a stronger breeze, letting you adjust the airflow to your comfort, whether you want a gentle wind or a powerful gust. But the real magic happens at the back of the motor, where things get even more interesting. A small extension of the shaft connects to the oscillation system, cleverly using the same spinning motion for another purpose. The motor's only job is to spin, but engineers found a way to use that single motion for two tasks: spinning the blades and powering the sweep, or oscillation, of the fan. Instead of adding a second motor, they cleverly redirect some of the spinning energy to drive the oscillation, making the design both efficient and resourceful. This keeps the fan simple, affordable, and reliable, so it can run for years with minimal maintenance. The motor just spins, unaware that its power is being split for two jobs, working tirelessly behind the scenes. Now, let's look at the part you control, the oscillation knob, a small but important feature. This simple switch lets you decide if the fan should sweep back and forth or stay still, giving you control over the direction of the breeze. It's a direct mechanical connection, no electronics needed, just pure engineering. Next, we'll see how this knob engages the oscillation system, setting the fan in motion across the room. Let's follow the power as it moves deeper into the fan, tracing the journey from the motor to the oscillation mechanism. The journey continues with the oscillation knob, unlocking the fan's full range of motion and comfort. On the top, or sometimes behind the fan, you'll usually find a small knob or button that controls the oscillation feature. It's often easy to spot, designed for quick access. Push it down, and you engage the oscillation, pull it up, and you stop it. This simple action gives you instant control over whether the fan sweeps side to side or stays pointed in one direction. This knob acts like a switch operator, connecting or disconnecting the spinning motor from the oscillation mechanism hidden inside the fan's body. When you push the knob down, it moves a rod that slides a small gear into place inside the gearbox, setting the oscillation system in motion. The gears mesh together, and the motor's spinning power is transferred to the oscillation system, making the fan head move smoothly from side to side. No electricity is involved in this part, just a simple physical link between the knob and the gears. Pull the knob up and the gear disengages, breaking the connection and stopping the oscillation instantly. The fan blades keep spinning, circulating air, but the head itself stops sweeping across the room. This push-pull mechanism is robust and reliable, giving you direct tactile control over the fan's movement every time you use it. You can actually feel the satisfying click as the gears engage or disengage, a sign of solid engineering. There are no circuit boards here, just sturdy, time-tested mechanical parts working together. That's why these fans can last for years, sometimes even decades, with minimal maintenance. Now that we've engaged the system, let's see how the gearbox transforms the motor's high speed into a gentle, controlled sweep. The next step, slowing things down for that smooth, relaxing oscillation. Let's open up the gearbox and take a closer look at what's inside. The secret to smooth oscillation is inside. Here's how it works and why it's so effective at creating a gentle breeze throughout the room. With the knob engaged, the motor's power flows into the oscillation system. But the motor spins fast, thousands of times per minute. If we use that speed directly, the fan head would whip around uncontrollably. Enter the gearbox, whose main job is gear reduction. Inside, the motor's shaft turns a worm gear, a screw-like rod. The worm gear spins a larger cogwheel, dramatically slowing the motion and increasing torque. For every full turn of the big gear, the worm gear spins many times. This trades speed for controlled, powerful movement. The output shaft now turns slowly, maybe one full circle every 10 seconds. This slow rotation is perfect for the fan's gentle sweep. Without gear reduction, smooth oscillation would be impossible. The gearbox tames the motor's energy, making the fan's movement calm and reliable. Now, how do we turn this slow circle into a back-and-forth swing? The answer, a simple offset pin. Let's see how it works. The next step is the offset pin. The gearbox's output shaft spins in a slow, steady circle, but we want the fan head to swing back and forth, not spin all the way around. The solution is an offset pin, a small peg placed near the edge of the spinning gear. As the gear turns, the pin traces a wide circle, like a dot on a spinning record. This pin connects to a rod. As the pin moves, it pushes and pulls the rod, turning circular motion into a linear back-and-forth movement. It's the same principle used in steam locomotives, but in reverse. The offset pin is the heart of the conversion from rotation to oscillation. This simple part drives the fan's side-to-side dance. Next, let's see how this motion is transferred to the fan head. The connecting rod, pushed and pulled by the offset pin, needs to make the fan head swivel. This is where the four-bar linkage comes in, a classic mechanical solution. The four bars are the stationary base, the pivoting neck, the connecting rod, and the crank, the gear with the offset pin. The connecting rod links the crank to a point on the fan's neck, offset from its pivot. As the crank turns, the rod pushes and pulls, making the neck swivel back and forth. The four-bar linkage constrains the movement, ensuring the fan head sweeps in a precise arc. The size of the offset pin circle sets the width of the sweep. It's a reliable, predictable system built from just a few sturdy parts. This mechanism keeps the fan's movement smooth and controlled. Now let's look at why the fan slows down at the ends of its sweep. The answer lies in the geometry of the linkage. Here's what happens. Ever notice how the fan slows down at the ends of its sweep? That's not a flaw. It's a result of the four-bar linkage and crank system. The offset pin moves at a constant speed, but its effect on the rod changes as it travels the circle. In the middle of the arc, the fan moves fastest. At the ends, it slows and reverses smoothly. This built-in slowdown prevents jerky movements and reduces stress on the parts. It's a natural, elegant feature of the mechanism. The fan's graceful motion is all thanks to clever geometry. Want the fan to stop sweeping? Just pull the knob. This lifts a gear inside the gearbox, breaking the connection between the motor and the oscillation system. The worm gear keeps spinning, but its teeth no longer drive the rest of the gears. The oscillation mechanism freezes and the fan head stays put. The blades keep spinning, blowing air in one direction. Push the knob down and the gears re-engage, restoring the sweep. This simple clutch system gives you instant control. It's practical, intuitive engineering. Let's put it all together. Electricity powers the motor, spinning a shaft. The front spins the blades, the back drives a worm gear. The gearbox slows the motion, turning a crank with an offset pin. The pin pushes and pulls a connecting rod, which moves the fan head through a four-bar linkage. The result? A smooth, sweeping motion, all controlled by a simple knob. No computers, just gears, pins, and levers. Next time you see a fan, remember the hidden genius inside. Simple parts, perfectly arranged, create something elegant and useful. It's a beautiful machine.